Hi there, Rachel Chase here, and in the next video of our two-sample hypothesis testing series, we will take a look at calculating hypothesis tests for two means that are independent. First, we should discuss what it means to be an independent sample versus a dependent sample. Independent samples have no influence over one another, and that's the biggest thing to keep in mind here. On the other hand, dependent samples have some type of interaction or some type of connection. For example, if you were to do a before and after type of hypothesis test, so perhaps it's a weight loss program and you were curious to see how body composition has changed over time, you would use dependent samples, which we'll discuss in a future video. If instead you're looking at maybe, let's say, two different classes worth of information where the students are different in each one of your classes, you would look at this as an independent sample. So let's take a look at how we would go about hypothesis testing here. Now, one thing that we've learned about with one sample hypothesis testing is you still have to verify, are you dealing with a sigma known or sigma unknown situation? Remember, sigma is your population standard deviation. So if you're in a case where you know the population standard deviations, then you would use a z-test. That's quite frankly very unlikely, which we're aware of from one sample testing. So in the situation where you have only sample standard deviations, you're going to use your two-sample t-tests instead. Let's take a look at an example. In a study of proctored and non-proctored tests in an online intermediate algebra course, researchers obtained the data for test results given below. Use a 0.01 significance level to test the claim that students taking non-proctored tests get a higher mean than those who take proctored tests. Now, given this information, we have our first group and our second group. They've also told us we want to test this at 0.01. And since sigma is unknown, see that we have our sample standard deviations here, we're going to use a two-sample t-test. Now, how do you go about setting up your null and alternative hypotheses in a case like this? Well, ideally, regardless of the type of class, the type of test, you would always think that your means are actually the same. So that students should be doing just as equally well whether they take a test in a proctored setting or a non-proctored setting or unproctored setting, however you want to phrase that. Now, this test is asking us to claim that students who take non-proctored tests get a higher mean than those who take proctored tests. So set up your means. Non-proctored is group 2, so that means mu1 should be less than mu2. Again, we're saying that those who take non-proctored tests do better, hence why the sign is going towards the non-proctored test. Now, from this, the process is still the same. When you're using your calculator, you can go find in your list your not regular t-test, but your two-sample t-test. And you'll notice just above that is the two-sample z-test. So again, you need to identify which is appropriate. So we're going to select option 4 here and go into stats. X bar 1 is our sample mean of the first, which is 74.30. Our sample standard deviation is 12.87. And our sample size is 30 for the first group. The second group has a mean of 88.62 with a standard deviation of 22.09 and a sample size of 32. And it's not a big deal if the samples are in fact different in size. Next here, you're going to find the hypothesis type that matches. We are testing that mu1 is less than mu2. Our data is not pooled, so you're going to go ahead and calculate. So what information does this give us? And you'll notice this information should all look very similar to stuff we've done in the past. So here we have a t-test statistic of -3.14 and a p-value of 0.0014. Well, if we're testing this at 0.01 level, our p-value is definitely smaller than alpha, which means that we reject our null hypothesis. We have sufficient evidence to suggest that students taking non-proctored exams score higher than those who take proctored exams. Now, something I want to take a moment to discuss here is this may not be the best measure of how students are really doing. If you take a look at the standard deviation of each sample here, you'll notice the standard deviation for the non-proctored group is almost double what it is for the proctored group. So although the mean is a little bit lower in the proctored group, the students scored pretty consistently, which means as a class, they were all roughly in the same area. Now, on the other hand, we have such a high standard deviation, 22, that's what, roughly about 25% of this. So your coefficient of variation is 25% in this sample, whereas over here, if you calculate it, it's about 17%. So while those might not be the best across the board, the first group that was proctored did actually score more consistently. Maybe not better as far as the class mean goes, but more consistently as a class, which also says something. While a hypothesis test is great and it can tell you information about, was one group stronger than the other? Sure. It's not necessarily the full picture. So you do have to keep in mind during interpretation how you can perform a hypothesis test, you can make a conclusion, but at the end of the day, you need to also bring in information about what you know from other aspects of stuff to really be able to make an informed decision about what's happening. Next, let's take a look at another example where we're dealing with independent samples. A person's body mass index is computed by dividing their weight in kilograms by the square of their height in meters. Given below are the BMI statistics for a random sample of males and females. Use a 0.05 significance level to test the claim that males and females have the same mean BMI. Something to point out here is to really verify that this data is in fact independent. And they start by saying this is a random sample. If they had made a comment that these are, let's say, married couples or those who are dating, you might even want to look at this as dependent samples. However, here, if they are both truly random samples, which is the assumption we are going on, we can use a test or a two-sample test with independence. So run through the information we already know about our samples, and they want us to test to see. Of course, we're going to assume that our population means are in fact the same. They want us to test to see if there is any difference, right? Do they have the same mean BMI? So that's your indicator for doing a two-tailed test. Okay? So go ahead, take a moment and plug this in your calculator. We also had our sample standard deviation like we did before, so we're going to use that, the t-test that is. And unlike before where we had a directional test, here you're testing that two-tailed. So same question as before. What information have we found out here? Not only is our test statistic quite large, but that is really massively far away from our data. So our t-test is 17.896, and our p-value is, holy cow, what, 27 zeros in front of this. So I would say it's safe to say that that p-value is approximately 0 at that point. Very, very far away. Or we can go ahead back and see, oops, we have a typo here, huh? Our mean of our second sample missed one of our 6s. So let's backtrack here. And while making a mistake like this is, in this case ended up being pretty obvious, right? We checked through our whole list. That's really something to be aware of, is go back and double check. As you can see, I skipped something over when typing it. All right, here we go. So now that we've gone back in and fixed our typo, we can see we have a much more reasonable t-score. So our t-test statistic is equal to 1.27, which really isn't that far out, and we have a p-value of 0.2066. Compared to our significance level of 0.05, we can say our p-value is greater than alpha, which means that we fail to reject the null hypothesis. In other words, we do not have sufficient evidence to suggest that there is any difference in the mean BMI of males and females, according to the sample information that we have tested. So when you're dealing with two sample tests and the data is in fact independent, you can always go back to your two sample t-tests. Similar to what I had said in the proportion video is, yes, of course, there are formulas for all of this. You can still use the tables, but in the real world, you're probably not going to be pulling out those tables, and you should be somewhat familiar with the technology. Similarly, if you do use something like Excel, Excel can calculate all of this for you, even without a stats package, and it also does provide you with the p-value. In the next video, we'll explore what happens when you're dealing with two means for dependent samples instead. Thanks for watching, and I'll see you there.